You know, usually when we talk about a medical diagnosis, there's this expectation of precision.
Right, yeah.
It's almost like mechanical engineering. I mean, you fall off your bike, you break your arm, the x-ray shows that jagged white line through the bone, and the doctor just points at it and says, there it is.
It's totally binary.
Mm-hmm.
It's broken or it's not broken.
Yeah.
It's clean, it's visible, and you get a cast.
Exactly.
You wait 6 weeks, and the machine is fixed.
And there is a real comfort in that, right? We like things to be visible. We like to categorize the human body as this machine with discrete parts that occasionally snap and can just be glued back together.
Yeah,
But the moment you step out of the orthopedic ward and into the world of advanced biotech or cellular reprogramming and neurodevelopment, that simple X-ray machine is just utterly useless.
Oh, completely. It's like looking at a different universe.
Right. We find ourselves looking at a diagnostic landscape that is just incredibly murky.
It is the absolute definition of diagnostic muddy waters. And that murkiness, that sheer complexity, is exactly why the source we are diving into today is so vital.
Yeah.
Because we are currently living through a transition period. We're moving from a world where medicine is just about fixing those visibly broken parts to a world where we're fundamentally rewriting the underlying software of the human body.
Which brings us to the core of today's deep dive. We are exploring a fascinating, highly structured document called the Century of Living Information Assay Spine.
Written by Zachary David Enfield.
Right, an independent researcher. And what makes this document stand out isn't just the subject matter, but its format. It is an essay spine.
Right, which sounds a bit academic, but it's really just...
It's an architectural blueprint for a massive thesis mapping out the next century of human biological and technological evolution.
And he's making an incredibly bold, overarching argument here. He posits that the defining shift of the 21st century is not merely that computers are getting smarter. I mean, we all know that's happening.
Yeah, that's old news.
Right. The real shift is that machine intelligence is gaining the ability to read, write, manufacture, gestate, repair, and eventually re-embody living biological systems.
So, if you're listening to this, you might be prepping for a tech meeting or trying to catch up on the bleeding edge of biotech, or maybe you're just curious about how long your physical body might actually last.
Which is a totally fair question these days.
Absolutely. So this document takes us from the dawn of public AI all the way to the literal engineering of human rebirth by the year 2100.
But before we get into the timeline, we have to establish the source's discipline.
Oh, yeah, the labels.
Yes. What makes this document credible isn't just its audacity, it's his strict, ironclad framework. He uses a 4-label system for every single claim he makes.
He absolutely refuses to blur the lines between what is happening today and what is just speculative fiction.
Right, which is so refreshing.
I found the system so helpful for cutting through the hype. Let's break down these 4 labels. The first is established.
Established, right.
These are peer-reviewed facts, regulated clinical uses, things we can directly observe in a lab or a hospital right now. There is no guessing here.
The second label is active research. So this means a concept has been demonstrated, but perhaps only in animal models.
Or like isolated cellular models.
Exactly, or very early, limited human trials.
Yeah.
The underlying mechanism is real and proven, but it still has significant engineering or regulatory barriers to overcome before mass deployment.
Right. Then we move to the third label, which is projection. This is where the author extrapolates from converging technologies.
It's basically an if-then scenario based on probabilities.
Yeah, like if technology A continues at its current pace and technology B matures, then scenario C is the highly probable outcome.
And finally, the fourth label is horizon.
Horizon.
Yeah, this is reserved for philosophical or engineering possibilities that have not yet been demonstrated in any physical way. They are hypotheses.
Educated guesses.
Right. And he's militant about this. You cannot present a horizon hypothesis as an established fact.
That discipline is crucial. When you start talking about extending the human lifespan to 150 years or transferring consciousness into a new substrate, it is so easy to sound unhinged.
Oh, totally. You sound like a sci-fi novelist.
Exactly. But by forcing every single idea into one of these 4 buckets, he builds a very sturdy, logical bridge to the future.
He explicitly warns the reader that the power of his timeline comes from the convergence of real bridges. It does not come from pretending we've already crossed the final one.
Right.
For example, he points out that current brain-computer interfaces do not upload minds.
They just read signals.
Right. Artificial wombs have supported premature animal fetuses, but they have not grown complete human beings from a single cell. We have to respect the actual physics of where we are.
So, keeping that strict four-label discipline in mind, where does this century-long transformation actually begin? Because if we are heading toward biological rebirth by 2100, there has to be a starting line.
There does.
What was the first spark that proved our biology could interface with our digital world?
According to this spine, the prologue to our entire century starts back in 2017. And it begins with a galloping horse.
The horse in the cell. I love this part.
Yeah, it's wild. This falls strictly under the established label. In 2017, a team of researchers, led by a scientist named Seth Shipman, used the CRISPR-Cas system to encode a short digital movie of a galloping horse into the DNA of a living population of bacteria.
Wait, a digital movie? Like pixels?
Yes. And then they successfully recovered the data back out of the bacteria. They essentially played the movie from the DNA.
Okay, let's unpack this because I
Yeah.
want to make sure I'm getting the analogy right. It's essentially like printing a Word document, but instead of using paper and ink, you are printing it into the molecular alphabet of a living organism.
That's a great way to think about it.
And the organism doesn't just sit there like a hard drive, it keeps on living.
Right. It divides, it replicates, it goes about its microscopic bacterial business, all while carrying your movie inside its genetic code.
To understand the gravity of this, we really need to look at the mechanics. They didn't just shove a microchip into a cell.
No, not at all.
They took a digital pattern, the binary code of pixels on a screen, and translated it into the nucleotide sequence of life, the A, C, G, and T of DNA.
Exactly. And the choice of the galloping horse is incredibly poetic, actually. It was an homage to Edward Muybridge's 19th century photographs of a galloping horse, which were essentially the first motion picture ever created.
Oh, wow. I didn't know that.
Yeah. Muybridge proved that a new medium photography could capture motion and time. Shipman's team used that exact same horse to prove that a completely different medium, living DNA, could capture and store digital information across time.
But how did they actually get the movie into the genome? I know CRISPR is involved, but usually we hear about CRISPR as a tool for cutting out genetic diseases, like molecular scissors.
Right, so CRISPR case is essentially an ancient bacterial immune system. In nature, when a virus attacks a bacterium, the bacterium uses CRISPR to snip off a piece of the virus's DNA and store it in its own genome.
Like a genetic mugshot.
Exactly like a mugshot. This way, if that virus ever comes back, the bacterium recognizes it and destroys it.
So it's a memory bank.
Right. What Shipman's team did was hijack this mugshot-taking mechanism. Instead of feeding the bacteria viral DNA, they fed it synthetic DNA sequences that corresponded to the pixels of the horse movie.
Oh, that is so clever.
Yeah. The bacteria's own CRISPR system grabbed that information and meticulously filed it away in its genome frame by frame over several days.
That is an incredible hijacking of a natural system. But I want to be very careful here about what this actually means. It's easy for the imagination to run wild.
And he is quick to draw the boundary. What this experiment proved is that a digital pattern can become nucleotide sequences, be inserted into a living genome, persist through living biological processes like cellular division, and eventually be read back into a recognizable digital form.
But it absolutely did not prove that the bacteria, understood the movie.
No. The bacteria wasn't sitting there enjoying a cinematic experience.
Right. It didn't digitize or transmit any form of consciousness.
Hmm.
As the author notes, data storage is not the same thing as identity.
Exactly.
This was simply a primitive witness of information crossing substrates. It was a proof of concept that the wall between electronic data and biological life is porous.
A galloping horse crossing an invisible border between the digital and the biological.
Yeah.
It's the perfect prologue, but it's just passive storage.
Yeah.
The real catalyst, the moment the world actually shifted on its axis and accelerated this entire timeline, was November 30th, 2022.
Oh, the dawn of public generative AI.
Right.
Now, to be fair, electronic computation has been utilized in medicine for decades. I mean, we've used computers for MRI imaging, for running statistical models on drug trials, for early genomics.
Sure.
The year 2022 did not invent biomedical computing.
No, it didn't invent the computation, but it completely democratized the interface.
Yeah.
That is the crucial distinction he makes.
Because before 2022, if you wanted to interrogate deep biological complexity, you needed a massive team. You needed specialized bioinformaticians, structural biologists, and coders who understood incredibly dense, specialized software.
Right. The bottleneck wasn't just the computing power. The bottleneck was human intelligence and the sheer friction of using the tools.
If you're listening to this, you likely remember exactly what it felt like when that interface changed. AI didn't suddenly wake up and cure cancer the next morning, but it acted as a massive accelerant.
It was like taking a supercomputer that previously required a PhD to operate and giving it a conversational interface so anyone could ask it questions.
It widened the bottleneck exponentially. Suddenly, millions of minds, researchers, medical students, independent thinkers gained access to tools that could synthesize vast amounts of scientific literature.
And generate complex code to model biological systems and spot patterns across disciplines that a single human mind could never hold all at once.
So, if 2017 proved we could put a digital file into a living cell, and 2022 gave millions of people the conversational AI tools to process massive amounts of biological data, what happens when we start using those tools not just to read data, but to actually write new biological software?
That transition leads us directly into the period of 2022 to 2030,
Okay.
where public intelligence learns to actively read and write life. And this isn't horizon speculation. This is firmly in the realm of established and active research.
Let's start with the reading part. Because reading biology isn't like reading a book. DNA is just the sequence of letters, but those letters don't tell you what the biological machine actually looks like or how it moves.
Exactly. The ultimate challenge in biology has always been the distance between a genetic sequence, the 1D string of DNA, and its physical 3D structure.
Right.
For decades, biology was plagued by something called Levinthal's paradox. It stated that because a single protein chain can fold into an astronomical number of possible shapes, it would take a supercomputer longer than the age of the universe to calculate the correct fold using brute force physics.
Wow.
Because of that, figuring out how just one protein folded used to take a scientist their entire PhD, using tedious methods like X-ray crystallography.
Because the shape of the protein determines what it actually does in the body, right?
Yes.
If it folds one way, it's healthy muscle tissue, but if it misfolds, it might become an amyloid plaque that causes Alzheimer's.
Precisely. Structure dictates function. And this is where AI fundamentally changed the game with systems like AlphaFold 3.
I remember hearing about
It
AlphaFold.
was huge. Instead of trying to brute force the physics of every atom, AI used deep pattern recognition across all known biological data to simply predict the final shape.
Just bypassing the math problem entirely.
Exactly. And AlphaFold 3 didn't just predict isolated protein structures, it predicted joint structures involving proteins, nucleic acids, small molecules, and ions interacting together.
That's a whole ecosystem.
Right. It gave us the master key to modeling interactions across the entire molecular system. It moved us from merely cataloging the 1D alphabet of life to actively reading its 3D grammar.
Okay, so we can read it. We can see how all the tiny molecular gears fit together in 3 dimensions. But the leap from reading to authorship writing new biological tools is where this gets genuinely disruptive.
And he points to some incredible milestones here. One of them is OpenCRISPR-1.
Which sounds like open source software.
It basically is. This was an AI-generated genome editor. An AI model was trained on more than 1 million natural CRISPR systems found across different bacteria in nature.
Get 1 million.
Yeah, it analyzed all those patterns, and then it essentially invented a brand new synthetic CRISPR system from scratch. And when they tested it, it successfully edited human DNA in human cells.
Think about that. Generative AI isn't just making pictures or writing emails anymore. It's generating functional, microscopic, biological machinery that never existed in nature, and it works perfectly.
It's astounding.
And this isn't just happening in a petri dish. The source mentions a very specific, grounded example from 2025 involving an infant with a severe condition called CPS1 deficiency.
Right. CPS1 deficiency is a rare, life-threatening genetic disorder. It affects the liver's ability to process ammonia, which means ammonia builds up in the blood to toxic levels, causing brain damage or death.
That's terrifying.
It is. The traditional medical approach for rare diseases is often to search for a mass-market drug that kind of manages the symptoms, or to put the patient on a highly restrictive diet.
Just managing the decline.
Exactly. But in 2025, they used a completely different paradigm. A patient-specific base editing therapy was designed and administered specifically for this infant.
I want to break down base editing because it's a crucial mechanism here. Traditional CRISPR is often described as genetic scissors, right? Like it makes a double-strand break, literally cutting the DNA ladder in half to disable a gene.
Yeah, it's quite violent at the cellular level.
But base editing is much more elegant.
Yes, base editing is more like using a pencil with an eraser. Instead of cutting the DNA ladder, the mechanism chemically alters a single nucleotide base.
So turning an A into a G or a C into a T.
Exactly, without breaking the DNA strand. It fixes the typo in the genetic code directly.
So imagine we have an encyclopedia with a billion words in it, and there's one single typo on page 500 that is causing this infant's liver to fail. AI helps design a bespoke molecular pencil that navigates to page 500, erases the wrong letter, writes the correct one, and leaves the rest of the book completely untouched.
Generated for one specific human body.
That just blows my mind.
This represents a monumental directional shift in medicine. We are moving away from picking a generalized product off a pharmacy shelf, which was designed for the statistical average of a population.
Right.
Instead, we are using AI to analyze a patient's specific genomic error, generating a custom biological tool to fix that exact error, and administering it. It is the dawn of true one-person medicine.
And what's fascinating is that this communication isn't just one way. We aren't just sending digital commands into biology to edit genes. The biology is increasingly speaking back to the digital world.
Right, it's the two-way street.
The author highlights a 2025 brain-computer interface, or BCI, trial that illustrates this perfectly.
Yeah, this is another crucial arrow in the timeline. In this trial, they used an intracortical BCI.
Intracortical, meaning inside the cortex.
Right. The sensors aren't just in a cap you wear on your head. Microscopic arrays are implanted directly into the motor cortex of the brain, physically resting among the neurons.
Wow.
For an ALS patient who had lost the physical ability to speak, this BCI read the neural action potentials, the electrical intent to move the muscles of the mouth and throat, and translated that directly into a synthesized voice with real-time expressive control.
It took the biological neural activity and translated it into digital language, fluently and instantly. No lag, no robotic misinterpretations, just thought becoming sound through a digital bridge.
So if we step back and look at the period approaching 2030, we have digital to biology translations, like the CRISPR therapies in the horse movie.
Right.
And we have biology to digital translations, like the intracortical BCI voice synthesis. It means the two directions are on a collision course. Intelligence is public, molecules are legible, we can generate custom biological tools, and we can translate brain activity into digital signals. The foundational pillars are all in place.
Which means we can start building. We can start looking at the natural world, not just as a zoo, but as a hardware store, a library of biological Lego bricks.
This is one of the most conceptually fascinating parts of the essay. He calls it nature's library of exceptions.
I love that phrase.
It's great. The premise is simple. If we want to solve human aging, radiation damage, and disease, we don't have to invent the solutions from scratch in a vacuum. Nature's already solved almost every biological problem. It just distributed those solutions across different species over millions of years of evolution.
Let's walk through this library, because the examples he pulls are just astounding. First up, the tardigrade.
Oh, the tardigrade. The water bear.
Yeah.
It's a microscopic animal famous for surviving environments that should instantly kill any living thing. The vacuum of space, extreme heat, extreme cold.
And lethal doses of radiation.
Right.
The source notes that the tardigrade has a unique protein called DSUP, which stands for damage suppressor. And under active research, scientists have actually used mRNA to deliver this DSUP protein into mouse tissues.
To understand how this works, we have to look at what radiation actually does to a cell. When ionizing radiation hits a body, it interacts with water molecules to create highly reactive hydroxyl radicals.
Which sounds bad.
It's very bad. These radicals act like microscopic shrapnel. They physically shred the DNA strands inside the cell's nucleus, causing massive mutations or immediate cell death.
But the DSUP protein acts as a physical shield. It binds directly to the nucleosomes, which are like the spools that DNA wraps around, and it physically blocks those hydroxyl radicals from reaching the DNA. When they put this into mouse tissues, it dramatically reduced radiation damage, while still allowing targeted tumor radiotherapy to work. I mean, we are borrowing a radiation shield from a microscopic water bear.
It's incredible. Then there is the axolotl, a type of Mexican salamander. It possesses an ability that seems like pure magic. It can regenerate entire lost limbs, portions of its heart tissue, and even parts of its brain.
But how does it know what to grow? I mean, if I cut off a salamander's arm at the elbow, it doesn't just grow a chaotic tumor of cells, it grows a perfect forearm, wrist, and hand with the exact right bones, nerves, and blood vessels.
Right.
How does the stump know it needs to build a hand and not another shoulder?
It does this through what biologists call positional memory circuits.
Positional memory.
Yeah. When an axolotl loses a limb, the cells at the site of the amputation revert into a mass of unspecialized stem cells called a blastema.
Okay.
But these cells maintain an incredibly precise 3D coordinate system. Through gradients of specific signaling molecules, Each cell somehow knows exactly where it is located on the body's X, Y, and Z axis.
So they basically have built-in GPS.
Exactly. Because they know their coordinates, they seamlessly rebuild the correct missing structure. And current research shows that these specific positional circuits can be experimentally identified and potentially reprogrammed.
We also have the bowhead whale, a mammal that can live for over 200 years without developing cancer at the rates humans do. How do they manage that with bodies so massive? I mean, more cells should mean more chances for cancer, right?
You'd think so, but their cells show unusually accurate DNA double-strand break repair. As humans age, our DNA accumulates micro tears and errors, and our repair mechanisms get sloppy.
Which leads to cellular dysfunction and cancer.
Exactly. But the bowhead whale essentially has a Tremium heavy-duty autocorrect for its genetic code. Research highlighted in the spine shows that when scientists isolated a specific bowhead whale protein called CIRBP and introduced it into human cells in a lab, it actually improved our human cells' ability to repair their own DNA.
So we have radiation shields from tardigrades, 3D coordinate regeneration from axolotls, and heavy-duty DNA repair from whales. The author also notes that we are attempting to build our own cellular machinery from the ground up, mentioning a 2026 preprint about something called Spud Cell.
Spud cell.
Right.
This falls under the transition to synthetic biology. Spud cell is described as a chemically defined cell-like system.
Cell-like, so not a real cell.
Right. It is capable of taking in nutrients, growing, replicating its synthetic genome, and undergoing genetically encoded division. It mimics the mechanics of life.
But I want to apply the discipline here because it's easy to assume we just created artificial life.
And we didn't.
Right. The author is very careful to note that Spud Cell is entirely dependent on externally supplied, highly specific chemical resources. It cannot survive in the wild. It is not autonomous life. It's essentially a programmable chemical machine that merely acts like a cell.
Exactly. It's a synthetic chassis.
But wait, if we take all these pieces, the tardigrade shield, the whale repair kit, the synthetic cells, aren't we just treating the human body like a Frankenstein scrapbook?
That is a very valid concern.
Like, how does sewing together all these random biological party tricks actually coalesce into a coherent, functional medical system for a human being?
That is the pivotal question of the entire text. You cannot just inject whale proteins into a human and expect them to live to 200.
Yeah, that sounds like a recipe for disaster.
It does. You need a systemic, integrated approach.
Yeah.
And that is exactly why he introduces his master framework for the year 2050. He calls it the 8R biological architecture.
It's the 8 R's.
Yes, it's a conceptual model for how you take all these disparate Lego bricks and turn them into a comprehensive lifelong maintenance stack.
I love a structural framework. Let's walk through these because if this is right, this is the blueprint for how a hospital visit will theoretically operate in about 25 years.
Okay, so the first R is read. This is the foundation. It means maintaining a persistent, continuous digital model of each individual body. We're talking continuous genomic sequencing, advanced biomarker tracking, and using systems like AlphaFold to monitor molecular drift in real time.
So you don't just go to the doctor when you feel a lump. Your biology is constantly being read and modeled against your healthy baseline.
Exactly. The second R is rewrite. This utilizes the AI-generated CRISPR and base editing tools we discussed.
The molecular pencil.
Right. If the read phase detects that a dangerous genetic mutation has occurred in a cluster of cells, perhaps a precancerous drift, the rewrite phase sends in patient-specific genetic tools to tune that sequence back to health before a tumor ever forms.
That is incredible. So what's the third R?
The third R is resist. This is preventative shielding, and this is where the tardigrade DSUP comes in.
Oh, the radiation shield.
Yes. Imagine you were about to undergo a harsh medical treatment, or perhaps enter a high-radiation environment like deep space. Before you are exposed, you deploy extremophile proteins to temporarily provide radioprotection and stress tolerance to your healthy cells. You preemptively armor the biology.
Okay, the fourth R is repair.
Repair. This is correcting the accumulated everyday molecular injury of living. Routine maintenance.
So this utilizes those heavy-duty DNA repair mechanisms we borrowed from the bowhead whale.
Exactly. To fix genetic fraying, combined with engineered immune cells to clear out localized damage.
The fifth R is regenerate. This goes beyond fixing a single cell. This is tissue and organ scale reconstruction.
Right, and this relies on mastering the axolotl positional memory.
Like the 3D GPS system.
Yeah, If a patient suffers massive trauma, like a crushed limb or severe hard tissue death, the goal is to trigger the body to form a blastema and seamlessly rebuild the missing structure natively, rather than just forming scar tissue.
The sixth R is rejuvenate. This involves fundamentally restoring a youthful cellular state. The source mentions a 2026 trial treating participants to rejuvenate optic nerve cells for glaucoma.
To understand this, we really have to talk about cellular aging. Over time, our cells reach something called the Hayflick limit. They stop dividing and become senescent.
Senescent cells are often referred to as zombie cells, right?
Yes, zombie cells. They stop doing their job, but they refuse to die.
Sounds lovely.
Yeah, and instead, they sit in our tissues and secrete inflammatory toxins that degrade the healthy cells around them, accelerating the aging process.
So rejuvenation involves partial cellular reprogramming, using specific transcription factors to roll back the biological clock of the cell, and targeted therapies to actively hunt down and remove those senescent zombie cells.
Exactly. Performing periodic, organ-specific age resets.
Okay. The seventh R is replace. This is for the catastrophic failures that you simply cannot repair or regenerate natively. This involves fabricating what fails using 3D bioprinting.
Patient-specific 3D-printed titanium cranial implants are already established medicine today.
Right.
But by 2050, he projects this ladder escalating from printed hardware to living tissue patches to fully vascularized, functioning printed organs grown from your own stem cells.
Completely eliminating the organ donor waiting list and immune rejection.
Exactly.
And we have to mention artificial wombs here, right? We mentioned the 2017 research supporting premature lambs in an extrauterine system.
Yes, by 2050, those bioreactors could be used as developmental manufacturing chambers, maturing those complex 3D-printed organs safely before surgically implanting them into the patient.
So that gives us 7 Rs. Read, rewrite, resist, repair, regenerate, rejuvenate, replace. But there is an 8th R.
The absolute frontier of this architecture, re-embody.
Embody.
This is the process of preserving identity across renewed substrates. It involves using those intracortical BCI decoders and advanced neural prostheses to maintain the continuity of consciousness when one substrate, one physical body can no longer carry the whole process.
That 8R stack is staggering. But it leads to a very obvious immediate question. If we actually apply this comprehensive architecture to a human being constantly reading, repairing, replacing, and rejuvenating their parts, it completely breaks our traditional linear understanding of aging.
It does.
If you continuously replace the parts of an engine, the engine doesn't really have an age anymore. So how do we even measure human life expectancy when this biological maintenance stack arrives in 2050?
This moves us into Section 3 of the spine. 2050, the separation of ages and the net gain. And this is where he offers a massive, crucial correction to how we normally forecast longevity statistics.
Because right now, if you look at the conventional demographic forecasts, like the Global Burden of Disease Baseline, they project that global life expectancy will rise from around 73.6 years in 2022 to roughly 78.2 years by 2050.
That's a gain of less than 5 years.
Right. It assumes a slow linear crawl.
And that baseline is probably accurate for a purely global average because it factors in war, poverty, geopolitical instability, and the incredibly unequal deployment of new technologies.
Yeah.
But he argues that it is a fundamental actuarial mistake to evaluate the efficacy of a new medical paradigm by dividing its benefits across populations who never received the technology.
That makes perfect sense. It's like evaluating the speed of airplanes by averaging it with the speed of people who are walking.
Exactly.
If you want to know how fast the plane goes, you only measure the people on the plane.
Exactly. The meaningful comparison is looking at the people who fully participate in the validated AI-assisted and bioengineered care stack versus comparable people who only receive the mid-2020s standard of care.
Right.
By isolating those populations, he breaks down the 2050 landscape into distinct projection tiers.
Let's walk through these tiers, cause the numbers escalate quickly.
The first tier is global convergence. This assumes uneven access, but large gains from generalized prevention and cheap AI diagnostics. For this group, life expectancy hits 85 to 95 years.
The second tier is broad advanced access.
Yes. These are people in well-funded health systems that widely deploy validated AI, continuous monitoring, early rejuvenation therapies, and routine 3D organ replacement.
They are getting access to most of the 8 Rs.
Right. Their projected life expectancy jumps significantly, reaching 95 to 115 years.
Then you reach the frontier cohort, full maintenance participants.
These are the individuals who enter continuous monitoring, targeted rewriting, and systemic repair before they experience any severe, cascading physical decline. Their trajectory is projected at 115 to 150 years.
150 years. That is nearly double the current global baseline. But he goes one step further. He defines a final, highly speculative tier.
The continuity or escape velocity minority. For this incredibly small cohort, he states there is simply no medically stable terminal age estimate.
Wait, no estimate at all.
Right. Why? Because they achieve what gerontologists call actuarial escape velocity.
Escape velocity.
For these people, the medical science is advancing faster than their bodies are deteriorating. Every time they approach a biological limit, a new generation of the ADAR stack arrives to push that limit further away.
But I want to pause here and ask what this actually feels like. Because right now, when I picture a 150-year-old human, my brain automatically extrapolates our current aging process. I picture someone who is incredibly frail, bedridden, practically turning to dust.
And that is exactly the paradigm that shatters. He provides illustrative functional equivalence tables to break this down.
Okay.
If you are 150 chronological years old, but you've only received moderate maintenance fixing things as they break, you might physically feel like a healthy 90 to 105-year-old today. You are still elderly, you are still physically limited, but you are highly functional.
But if you've received strong rejuvenation therapies, if you have been systematically hunting down those senescent zombie cells and rolling back the biological clock of your tissues at chronological age 150, you might feel physically like a 72 to 90-year-old.
And if you are part of the re-embodied cohort, meaning your failing parts have been systematically swapped out for lab-grown, 3D printed organs, your vascular tissue has been regenerated, and your structural frame has been renewed at chronological age 150, you could possess the physical mobility, the cardiovascular resilience, and the organ reserve of a 25 to 55-year-old.
Think about that for a second. Your entire concept of middle age completely dissolves. You could be celebrating your 130th birthday and then going for a 5-mile run with the joints, the lung capacity, and the metabolic rate of a 30-year-old.
It's wild. Age ceases to be a single number.
It separates into multiple distinct clocks. You have your continuity age, which is how long you have subjectively experienced the world. But then you have your organ age, your immune system age, and your structural body age.
They're no longer tethered together in a linear collapse. You could possess a 25-year-old reconstructed physical body carrying a century and a half of subjective memories.
But this raises a massive fundamental red flag for me. I understand replacing a femur. I understand printing a new kidney or using a bioreactor to grow a new liver. But what about my brain?
Ah, yes, the brain.
If my physical brain is 150 years old, isn't it eventually going to succumb to Alzheimer's or dementia or just the physical thermodynamic limits of neural tissue? No matter how many tardigrade shields or axolotl tricks we use, the brain is trapped in that skull, accumulating 150 years of metabolic waste.
You have just hit the exact ceiling of the 2050 framework, and he acknowledges this completely. Biology has hard, inescapable physical limits. You cannot simply 3D print a brand new brain, toss the old one in the trash, and stick the new one in your head.
Because your brain is you.
Exactly. The connectome, the specific synaptic weights, the localized chemistry that is the locus of your identity, if you destroy that specific organ, you destroy the person.
So if the brain inevitably fails, the whole 8R stack fails with it. You just end up with a perfectly healthy 25-year-old body carrying a brain-dead 150-year-old mind.
Exactly. Which is why the timeline must push past mere bodily maintenance and into the incredibly wild, deeply speculative frontier of the year 2078. Section 4. Beyond cyberpunk and continuity engineering.
2078. I love that he explicitly chose that date. It's 1 year past the setting of the famous sci-fi video game, Cyberpunk 2077.
That is a deliberate statement.
He is essentially saying, let's take the dominant sci-fi tropes of immortality and let's critique them based on the actual mechanics of biology and physics.
Right. And when we think about living forever in modern science fiction, we almost always default to the tropes seen in Altered Carbon or Cyberpunk.
Yeah.
The underlying mechanism is always a digital stack or a memory chip implanted in the neck. The idea is that your consciousness is just data. When your physical body dies, a technician simply pulls the chip out, copies the data file, and pastes it into a brand new synthetic body, a sleeve.
It's the ultimate copy-paste solution to mortality. But he argues that this is structurally and philosophically flawed.
It is fundamentally flawed because it ignores the difference between copying and subjective continuity. Imagine we build a machine that can scan your brain perfectly, down to the quantum state of every electron.
Yeah.
We scan you, the machine destroys your original body, and it builds a perfect duplicate of you across the room. That duplicate will wake up, look around, and genuinely believe it is you. It will have your memories of stepping into the scanner. Your family will embrace it. Society will legally recognize it.
But from my subjective perspective, the original me, I died. The lights went out in the scanner and they never came back on. A perfect duplicate is just the second person who happens to share my history. It doesn't save me. This is the classic teleportation paradox.
Precisely. Therefore, if the goal is true, subjective survival, transferring a mind, cannot be a sudden upload. It cannot be a copy-paste event after physical death. If we want to survive the failure of our original brain, we have to engineer a gradual, unbroken bridge of biological continuity.
And this leads to his theoretical model for 2078, the A to A plus B to B continuity model. We are crossing firmly into the horizon label here, but the engineering logic behind it is fascinating. Walk us through how this slow migration would theoretically work across these 5 stages.
Stage 1 is capture. The original brain, let's call it brain A, remains completely conscious and physically active in the original body. Simultaneously, its incredibly rich neural activity is continuously read and decoded by extremely advanced, high-bandwidth intercortical BCIs.
So the person remains entirely anchored in brain A, experiencing the world normally.
Right. Stage 2 is coupling. That digital bridge reading brain A begins to transmit signals to a second, highly plastic living brain, brain B.
And brain B could be a lab-grown neural substrate, cultured from the patient's own reprogrammed stem cells, housed in a supportive bioreactor.
Exactly. The key here is establishing bidirectional communication. One unified operating system begins to span across 2 physically separate substrates.
Stage 3 is entrainment. This is the critical mechanism. Brain B is not just acting as a hard drive receiving a data download. It is learning through active closed-loop training.
Right. Every time brain A processes a visual stimulus or retrieves a memory, the digital bridge forces brain B to fire in a mirrored synchronous pattern. Because brain A and brain B are wired together bidirectionally, they begin to act as one highly distributed network. The continuity of consciousness stretches to encompass both substrates.
Stage 4 is distribution. After sufficient entrainment, your cognitive operations are fluidly spanning both brains. Imagine you recall a vivid childhood memory of riding a bike.
Okay.
The actual physical firing of the neurons retrieving the visual imagery might be happening in the lab-grown brain B, but the emotional processing and the motor cortex impulses are happening in your original brain A.
Right. The locus of your identity is no longer confined to the skull, it is distributed across the network.
And finally, stage 5 is migration. Over months or years, functional responsibility is slowly, meticulously shifted toward brain B.
The original biological tissues in brain A are allowed to gracefully degrade or are deliberately quieted, while brain B takes on the full cognitive load. Only after brain B is fully and seamlessly managing the continuous conscious experience is brain A eventually disconnected.
It's the ship of Theseus applied to the human mind. Think of it like riding a bicycle while slowly, piece by piece, replacing every single part of the bike.
That's a perfect analogy.
First, you swap the handlebars while still steering. Then you replace the chain while still pedaling. Then the front wheel, then the frame. You do all of this without ever stopping your pedaling or losing your balance. By the end of the journey, you are riding a totally new bicycle, but the ride itself never stopped.
There was no single moment where you got off one bike and onto another.
Exactly.
The A to A plus B to B model rigorously avoids a single abrupt replacement event. His horizon claim is that if the original conscious process remains uninterrupted and active, while the receiving biological network becomes progressively indispensable to that exact same process, the event is closer to a migration of state than a duplication of data.
But the author is very strict about his labels here. He notes, and I quote, "Science has not demonstrated this."
No, not even close.
He acknowledges that we don't even fully understand how consciousness emerges in one brain, let alone how it could span 2. His task in this essay is simply to define the architectural experiment that would one day distinguish true continuity from a sci-fi copy.
And to make this physical bridging connection theoretically possible, he introduces one of the most conceptually wild horizon hypotheses in the entire document. It's called the amyloid prion SUP35 wheat scaffold hypothesis.
Okay, I have to admit, when I first read the word wheat in a section about transferring human consciousness, I had to reread the paragraph 3 times.
I know, it sounds absurd.
We are talking about the bleeding edge of neurobiology, and suddenly we are talking about bread. Let's unpack this very carefully, separating the established biochemistry from the speculative application.
Let's start with the established biology, specifically prions. When the general public hears the word prion, they immediately think of devastating diseases like mad cow disease. A prion is essentially a misfolded protein that acts as a template, forcing other healthy proteins to misfold in the same way, creating a destructive chain reaction.
But he points out that there are functional prions in the human body, right?
Yes. Research over the last 2 decades has demonstrated that certain prion-like proteins in the brain, such as CPEB or ORB2, actually serve a vital function.
What do they do?
Because prions are incredibly physically durable and resist being broken down, the brain uses them to participate in persistent synaptic changes. They essentially create durable, structural local anchoring for long-term memories of the synapse.
Oh, wow. Second established fact, functional amyloids. Amyloid fibrils are another type of protein structure that we often associate with Alzheimer's plaques. But structurally, they are incredibly stable, self-assembling biomaterials. They act like microscopic, indestructible biological rebar.
Right. Third established fact, wheat gluten fibrils. Research highlighted from 2025 demonstrated that specific proteins found in wheat, specifically gluten, gliadin, and glutenin, can be chemically induced to form amyloid-like fibrils.
Wait, really?
Yeah. Because of the natural elasticity of gluten, these engineered fibrils have highly turnable structures. They are cheap, abundant, and can be engineered into bulk, durable physical scaffolds.
Okay, so we have functional prions that naturally anchor memories, we have amyloids that act like biological rebar, and we have highly elastic, tunable wheat fibrils. That is all established biochemical science. What is the speculative horizon leap that brings them all together?
The leap is the conceptualization of an engineered aromatic lattice. He hypothesizes that a massive physical scaffold, potentially derived from these tunable wheat and prion components, could be designed to safely interface deeply with living neural tissue.
Because it mimics the brain's own durable memory anchoring structures, the brain might accept it.
Right. This scaffold could then be seeded with optical or electronic sensors.
Essentially, he is proposing that we could use engineered wheat-derived fibrils as the physical molecular scaffolding to physically wire brain A and brain B together during the entrainment phase.
Exactly. But he issues a massive bolded warning in the text. He says, none of this proves that a SUP35 or wheat-derived lattice can carry consciousness.
It is merely a proposed molecular layer in a much larger theoretical neural continuity system.
Yeah, it is simply an idea for the hardware that might facilitate the bridge.
It is brilliant, wild speculation grounded in real granular chemistry. But exploring the mechanics of this bridge forces us to realize something profound. If humanity actually achieves this A to B migration, we are no longer just practicing medicine.
We aren't just fixing a broken bone or curing a genetic disease.
No, we are fundamentally altering the structural definition of what it means to be a human being in society.
Which brings us to the final act of the spine, Section 5, 2100 Rebirth as Infrastructure, Theology, and Failure Modes.
If the 2050 stack gives us biological maintenance and 2078 gives us conscious migration, what does the world actually look like in 2100 when this becomes everyday integrated infrastructure?
The author asks us to visualize a specific person living in the year 2100. This person has a continuity age, a subjective experience of the world of 178 years.
Okay.
However, their current neural substrate, their migrated brain B, has a biological age of only 39, and their structural physical body age is 24.
Wow.
They are supported by 3D printed organs, entirely regenerated vascular tissue, and a perfectly corrected AI-monitored immune system.
They possess memories spanning nearly 2 centuries, spread across multiple physical embodiment. The sheer societal weight of that reality is staggering to contemplate. Think about the legal system. How does a court of law distinguish between a true continuous person, an illegal digital copy, a fork in consciousness, and a legal successor?
It shatters our entire current legal and economic paradigm. Consider property rights. Who legally owns the original body if the consciousness successfully migrates to a new one, but the old body is kept biologically alive on life support?
That sounds like a legal nightmare.
It is. What happens to the concept of inheritance and generational wealth if a patriarch never technically dies, but just moves substrates every 80 years? How does the concept of a pension or retirement work when one continuous life contains 3 entirely different 40-year careers?
And what about family formation? We touched on artificial wombs earlier. By 2100, advanced extrauterine gestation could completely separate the act of gestation from the female human body.
Yes.
You could have couples monitoring and genetically correcting congenital diseases in a bioreactor over 9 months, interacting with the developing fetus digitally before the child is even born into the physical world. It redefines the timeline and the physical burden of reproduction completely.
And because of the overwhelming magnitude of these societal changes, he does something very interesting for a highly technical document. He concludes with a philosophical and theological chapter titled Yehi Or, When Information Takes Flesh.
Yehi or, which is the Hebrew phrase from Genesis for let there be light.
Yes, he is arguing that by the year 2100, rebirth is no longer a spiritual metaphor, it is a literal engineering reality, and that requires a new vocabulary to process.
Right.
In this chapter, he attempts to map ancient theological concepts onto this new infrastructure. He interprets light as intelligible order or operative information, the structured data of the mind.
Okay.
The word is the generative command, the AI-generated code that enters matter and produces biological organization. Spirit is the animating current, the physical electricity of the nervous system. And the soul is the individuated locus at which that continuous current acts as an eye.
I want to be very clear about something the author emphasizes here. He isn't saying that science somehow proves theology.
Not at all. He is incredibly strict about maintaining that boundary. Claims about the existence of the soul must be argued philosophically. They shouldn't be smuggled in as settled empirical science.
Yeah.
But he powerfully points out that the scientific narrative of continuous migration across newly generated bodies supplies a startlingly literal material vocabulary for ancient religious concepts like incarnation, breath, and physical rebirth. The religious and spiritual traditions of the world are going to have to deeply engage with these engineering realities because they are going to happen.
It's a profound synthesis. But as with any visionary architectural document, the strongest, most credible arguments are the ones that explicitly outline exactly how they could fail. We have to look at the skeptic's view. What are the systemic failure modes for this entire 21st century spine? What breaks the timeline?
He lists several massive systemic barriers. First, the cancer risk inherent in the ADAR stack.
Yeah, that seems like a big one.
When you aggressively use cellular reprogramming, introduce extreme regenerative capabilities, and artificially lengthen telomeres to rejuvenate tissues, you run the massive concurrent risk of promoting uncontrolled cell growth.
You are essentially giving cells the permission to divide endlessly.
Right. If you do not pair those rejuvenation therapies with absolutely perfect, infallible tumor surveillance, the treatment will cause aggressive cancers that kill you faster than natural aging would have.
Then there's the sheer complexity of the brain migration. We talked about entraining brain B. But a connectome, a perfect map of the physical wiring of the neurons, might not be enough.
That's a huge unknown.
What if dynamic chemistry, the precise millisecond timing of the glial cells, or the hormones constantly pumped from the gut of the physical body, are fundamentally required for consciousness to cohere?
Exactly.
If you successfully migrate the electrical wiring of the brain, but you lose the specific, messy chemical soup of the original gut and endocrine system, does the subjective I actually survive the transfer?
There is also the severe risk of synthetic biological escape. Programmable biology, like those chemically dependent spud cells we talked about, are designed to be safe. But biology is notorious for finding a way.
It always does.
If engineered cells or AI-generated extremophile proteins evolve or escape their intended function and enter the natural ecosystem, you risk a cascading biological catastrophe. You have to build in flawless kill switches and permanent resource dependencies.
And finally, there is the social failure mode, the risk of profound, insurmountable inequality. If this ADAR stack and continuity migration is only financially available to billionaires and political elites, we don't just get a wealth gap, we get a literal biological class system.
Yes, we create a world populated by immortal, continuously rejuvenated elites ruling over a short-lived, biologically frail underclass.
The author strongly argues that engineering democratic access is as much a technical hurdle as inventing the CRISPR therapies in the first place. But I want to push back with the ultimate existential question for this entire thesis. What if the brain continuity part, the A to B migration in 2078, is just fundamentally impossible? What if the laws of physics or the nature of consciousness dictate that the mind is permanently locked into substrate A, and when that specific biological brain finally succumbs to thermodynamic decay, you are gone forever? What happens to the entire 21st century vision then?
He addresses this head-on in his conclusion. It's his ultimate defense of the timeline.
He argues that even if the full horizon vision of conscious migration across substrates entirely fails, the partial gains of the 2050 8R stack will still permanently and completely transform the human condition.
That's a powerful point. Even if we can't move our minds to a new brain, achieving routine cancer resistance, having failing organs seamlessly replaced by 3D printed replicas grown from our own cells, and undergoing targeted cellular rejuvenation to clear out senescent zombie cells, that still delivers a world where people are living vital, incredibly healthy, highly functional lives well past 120 years old.
It still fundamentally eliminates the slow, degrading frailty of old age as we know it today.
Exactly. The baseline human condition is permanently altered, even if we never achieve true escape velocity. The decay of the physical body is successfully reframed from an unquestioned, terrifying sovereign that rules over our destiny into a difficult but ultimately solvable engineering problem.
This has been an incredibly damn fascinating journey. We started with the humble prologue of a grainy digital movie of a galloping horse encoded into bacterial DNA in 2017, proving that the digital biological border was porous.
We explored how the generative AI breakthrough of 2022 shattered the structural biology bottleneck. We broke down the massive integrative biological tech stack of 2050, from tardigrade radiation shields and axolotl regeneration to bespoke CRISPR base editing.
We ventured into the wild, deeply speculative frontier of continuous brain migration via engineered molecular scaffolds in 2078.
And we ended with the profound societal, legal, and theological ramifications of a world in 2100 where rebirth is medical infrastructure.
It is a century defined not just by humanity learning to live with information, but by information literally becoming living flesh.
And as we wrap up today's deep dive, I want to leave you with one final provocative thought to mull over on your own. We've talked a lot about the legal and spiritual rights of a continuing person spanning multiple centuries in physical bodies. But consider a concept the source briefly mentions regarding forked identity.
Oh, this is a mind bender.
Imagine we reach that 2078 continuity frontier. Your subjective identity and your memories become distributed across a living biological brain and a massive continuous digital backup infrastructure. Now imagine a catastrophic event occurs, a fire, a localized EMP, a severe physical trauma. The monitoring system concludes that your biological body has suffered terminal damage.
Right.
So it initiates the emergency protocol, severs the connection, and forces your continuous consciousness to restore from the digital bridge into a newly grown, waiting biological embodiment.
The monitoring system made an error.
A fragment of your old biological embodiment, containing enough of your original brain to maintain consciousness, actually survived the catastrophe.
No, there are two of you.
Your new embodiment, fresh, complete, and legally activated, and a surviving damaged fragment of your old embodiment trapped in the rubble. They both look around. They both vividly possess your memories up to the exact millisecond of the accident. They both look in the mirror and subjectively feel like I.
Yeah.
If those two diverging versions of you disagree on which one has the legal right to your bank accounts, your physical home, your children, and your soul, who wins? Who gets to be the real you?
It's not just a late-night sci-fi thought experiment anymore. By the end of this century, it might just be a standard case in family court.
Thanks for taking the plunge with us today. Keep diving deep.